today's lecture. Okay, so I will state monotone convergence theorem. All right, so let's H1 of t, H2 of t, etc. be a monotone increasing sequence of non-negative as I indicate here, right? Because they're all upper bound, lower bounded by 0, so they are non-negative and integrable functions, okay, on an interval I of the real line okay, right, so we have a monotone increasing sequence of functions, and these functions are non-negative and integrable on an interval. Okay, so the interval can be finite interval or infinite interval, okay, of the real line. Okay, and which converges to h of t for all t in the i.e. the limit of h n t for n goes to infinity is equal to t. Okay, so for each t, for each t, h1 of t, h2 of t is an increasing sequence of non-negative numbers, okay, and they approach to h of t. Okay, so what we have. Then as we know that each s sub n of t is integrable over on the interval, right? So this integral exists. Okay, and if we take the limit, okay, you take the limit of the integrals. Okay, so for each literal n, we have an integral. So this is a non-negative number. Okay, and this negative number, of course, because h sub n is an increasing sequence of functions. So as n go up, this integral go up too. Okay, so of course that this is a sequence of non-negative numbers, and its limit exists, and this limit will be would be the integral of h of t. Maybe I will say two things. Then h of t is integrable. Okay, on I, and the limit is equal to its integral. Okay, and because h of t is the limit of h of n, so we can write this as here. Okay. Right. So this identity shows that the operation of limiter and the operation of integration can exchange the order. Okay, they can exchange order under this circumstance. Here means that we have a monotone increasing sequence of non-negative integrable functions, h1, h2, etc., on an interval. Okay, and we know that this sequence of functions has a limit, right, for each t in the interval. All right, so h of t is a function. Then h of t is integrable on I, and we have this identity. Okay. All right, so it's a famous theorem in analysis, and we call it as monotone convergence theorem because it's a monotone increasing sequence, and this sequence converge. Okay, converge to a function. Okay, and under this circumstance, we have this conclusion. Okay. Right. So later on, you can use this important theorem. Now we will prove lemma 5.2.1 in the textbook. So for any non-negative random variable x, okay, the expectation of x, all right, can be expressed by this integral, and the integrand is a function of t, and this function of t is just the probability of the event that quantum variable x is greater than t. Okay, and so in terms of distribution function, okay, so this probability actually is 1 minus the CDF of the random variable x. Okay. Where is the CDF of x? Okay. Now the proof will have 2 steps, right? So we proceed in 2 steps. Step 1, okay, x is a simple non-negative random variable. Okay, with values say x1, x2 up to xn. Okay, so it has m values for some n in the natural number. Okay, in the set of all natural number. Okay, so this is a very restrictive case, right? X is just a simple non-negative random variables. So by definition, because simple random variable is a kind of discrete random variable. So and also that would be I from 1 to n, and x sub I, probability that x equal to x sub I. Okay, so immediately we can write down its expectation. Okay, so that is very simple. And when we look at this, so now we will draw a diagram. Okay, so suppose that this is x1, x2. Okay, and so suppose, assume n equal to 4. Okay, so we have, all right, and so we can write down the, okay, we'll go to here, circle, and with 1. So all right, so we draw the CDF of this simple random variable. Okay, and so so the jump here is probability that x equal to x1, and the jump here is probability that x equal to x2, and the jump is probability x equal to x3, and here probability of x is equal to x4. Okay, right? Now, and we can see that the sum can be regarded as the area. So that if we think about xi to be the length and the jump as the width, so this one, this area, so this area is x1 times probability of capital X equal to x1, and this part. Okay, so this part is so now the length would be x2, and the width is probability of x equal to little x2, right? And up to, so here, okay, so this one is x3, probability of x equal to x3, and finally this one, so here is x4, because the length is x4, right? And the width is probability that capital X equal to x4. Okay. All right. So expectation of x is the area of the shaded region. Okay, so it's the area of the shaded region. All right, so we look at it in this way. But now we can compute the same area. This is we add the area we add it's by using a horizontal strip, right? 1, 2, 3, 4, right? So we have 4 strips. All right, we have and the total area is the area of these 4 horizontal strips. But now we can recompute the same area vertically, right? So we can integrate the area, and so if we integrate that, we can see, okay, so that this is equal to so we can see that so I from 1 to it's xi p from 0 to xi, and well, I think I just read it to be okay. So this is equal to from 0 to infinity, and the summation of xi greater than or equal to t, and probability of x equal to xi, and this is dt. Okay, so you will see that the function. Okay, so the when you see it, maybe I will do it one by one. So you will see that from so vertically, let's see. I need another color. Okay, here. So I think we were okay. So this part, the vertical strip, first one, and the second vertical strip, and the fourth vertical strip, and the last vertical strip. Okay, so we have 4 vertical strips. Okay, and so actually this is becomes to summation of we can think about that from 0 to x1, and the function would be summation of probability so well, I think it's just we just write down probability of x greater than equal to t will be enough, because at every t here, the height is actually is that the probability of x greater than equal to t. I'm sorry, x greater than t here. Okay, so that in here, because when t is in between 0 and the x1, okay, because it's already very elementary. I don't know how to. But if you really want to do it, that's fine. 0 to x1, and this is for every t in between 0 and the x1. Okay, we know that this would be the probability that x is equal to x1 plus probability of x equal to x2 plus probability of x equal to x3 plus probability of x equal to x4. Okay, and the dt plus from x1 to x2. So in this segment, now there are on the height will be probability of x equal to x2 plus probability of x equal to x3 plus probability of x equal to x4 dt. Okay, and from x3 to x4, all right, the height it's probability of x equal to x3 plus probability of x equal to x4 and dt. All right, and the last strip will be x sorry, second, third, and x3 to x4. So this is probability of x equal to x4 and the dt. Okay, and then that's it. Okay, and when you look at this one, okay, when t is between 0 and x1, okay, but not include the x1, you can see that this is equal to probability of x greater than equal to t. Okay, and similarly, in this interval from x1 to x2, okay, so this is also equal to probability that x greater than equal to t. Because when t is here, x greater than x1, but in between x1 and x2, you can see that this jump is not included because t is already greater than x1. So x1, this jump will be left behind. Okay, and so we have this same. All right, and similarly, from x2 to x3, okay, the height, this sum is equal to probability of x greater than t. Okay. And finally, this is also equal to x greater than t. Okay. So you can see that we can use this probability. All right. So the integrand share the same. They actually they are from the same function. Okay. So actually they are the same function. Okay. All right. And so we can and of course that the last one is x4 to infinity, right? And this will be 0 and dt. Okay. And this 0 is equal to also is equal to x greater than t. Okay. So if x greater than x4, of course, then because x has value x1, x2, x3, and x4. So x4 is the last possible value, and so in this range, this probability is 0. Okay, this is 0 too. All right, so combine together, so we can write it down from 0 to and t and dt. Okay. Okay, so we establish this identity, all right, for simple non-negative. Okay, so for simple non-negative random variable. Okay, this is the first step. All right, and now we have step 2. Okay, now x is an arbitrary. So x is an arbitrary non-negative random variable. Okay, so now we let be a monotone so be a monotone increasing sequence of simple random variables, okay, which converges to x. Okay. All right, by proposition 5.2.c. Okay, so in proposition 5.2.c, we know there exists a monotone increasing sequence of simple random variable which converge to x. Okay. Okay. And so in here, now for each, then by step 1, because each x sub n is a simple non-negative random variable, so expectation of xn is equal to probability xn greater than t and dt. Okay. Right, so this is from the step 1. And on the other hand, or I just say, and since xn go up to x, okay, so for any t greater than 0, we have x1 greater than t will be this event, will it be a sub-event of x2 greater than t, okay, because x2 is greater than or equal to x1. So if x1 is greater than t, then x2, of course, is greater than t. Okay, so that this is a bigger one. Okay. Okay, so now we have okay, which is a monotone increasing sequence of events. Okay, right. So we have a monotone increasing sequence of events. Okay, for any t greater than 0. Okay. Right, and we know that x greater than t is equal to the union of xn greater than t. Okay. Because that xn will increase and the limit of xn is equal to x, so that x greater than t, this event is equal to the union of this event. Okay, but the union of this event is the limit of this monotone increasing sequence of events by our definition. Okay. Okay. Any questions? Remember, each event is a subset of the sample space, right? So when you say that this is subset is included in this subset, it means that for every outcome in this event will be an outcome in this event, right? So that it's easy to justify that. So maybe if you want to justify it, you can say omega is in the event. Okay. If omega is an outcome in this event, that means that xn omega is greater than t. Okay. Because that this event will consist of all outcome such that this is true, such that the value, right, of x sub n at this omega is greater than t. And this implies that xn plus 1, so the xn plus 1 omega we know this is greater than t, right? So x sub n plus 1 omega greater than t. So that means that t is in xn plus 1 omega greater than t. Okay. Oh, sorry. Omega. So every outcome in this event implies that it is in this event. So this is bigger. This is bigger. Okay? This is bigger. And similarly, you can prove the identity, the equality. And to show that the equality, you have to show the two directions. So you have to show it's a subset of this union. And on the other hand, the union is a subset of this event. Okay, so you can try at home. Okay, with the same method. So to show two set, we know two sets A, B have A equal to B, if and only if A include B. So A is included in B and B is included A. Okay, so to establish the equality of two sets, usually you establish these two inclusion relationship. Okay, it's usually so you have to show. So I encourage you to verify this is indeed the equality. Okay, by first shows that this event, okay, is included in this union. On the other hand, this union is included in this event. Okay. All right. So I will not go to detail. And so with that, so by the continuity of the probability function, P, okay, we have the probability of x greater than t is actually equal to the limit of the probability of xn greater than t. Okay, so that is from the continuity of the probability function. Okay. Right. So if this event is the limit of this monotone increasing sequence of events, then the probability of this event is equal to the limit of the probability of the event of the sequence of events here. Okay, so that is the continuity of probability function. So we have that. So this function, you can regard this as a function of t, and this is also a function of t. Okay. Okay. All right. So now, okay. Now, also note that the probability of x1 greater than t is because of this sequence, right? So we know that this is less than equal to probability of x2 greater than t, etc. Okay, and this is 0, right? So it's a monotone increasing sequence of non-negative functions. and integrable. Okay, because it integrable, right? Okay. Functions on the interval which is from 0 to infinity. Okay. Right? Okay. The event is become bigger and bigger, so the probability of the event become bigger and bigger, right? For each t. So it's a monotone increasing sequence of non-negative integrable function, and also its limit is POT. So now by the beginning, by the monotone convergence theorem, okay, so monotone convergence theorem, I just stay there. This integral, so this integral exists, okay, and this integral, because this is the limit of probability of xn greater than t and goes to infinity. So you can think about that. This is actually h of t, and this is h sub n of t. Okay. Okay. And so we can exchange the limit and the integration. Okay. Okay. And this is the expectation of x sub n. Okay. And by definition, the limiter, because we use this monotone increasing sequence of simple non-negative random variable to converge to this arbitrary non-negative random variable x. So by definition, we know this is equal to expectation of x. Okay. Okay, and so we have done. Because then we proved that the expectation of x is equal to this integral. Okay, and also we resolve our question that if we use different monotone increasing sequence of simple random variable to converge to x, suppose we have another sequence. You can see that. So if you have another one, say if you have use another sequence, say y1, this is y2, etc. Okay, and so you have yn, and this is yn. Okay, so you replace xn by yn by another monotone increasing sequence of simple non-negative random variables yn. Okay, so you can do it, and y1, etc. Okay, yn. Okay, and this is yn. Okay, and this y1, etc. And so the same, because that the limit of probability of yn greater than t, right, will be equal to probability of x greater than t. Okay. So, and this is yn. Okay, so you can see that the limit of the expectation of yn goes to this integral. The limit of the expectation of xn also goes to the same integral. Okay, so they have the same integral here, right? So our definition by using arbitrary any one of the monotone inclusion sequence to converge to x will be good enough. Okay, equal to expectation of x. Any questions? Okay, any questions? Okay, so we have proved this lemma already. Okay, we have proved this lemma already. So now we have. So let me remark a little bit. So I will say the above lemma. All right. Also shows that the definition, okay, of the expectation E x of a non-negative random variable x is independent of the selection of the approximation sequence okay. All right, so we have proof how to compute the expectation of a general non-negative random variable. Okay, so this non-negative random variable x may be discrete or may not be discrete, may be continuous or may not be continuous. That's arbitrary. Okay. All right, now our mission hasn't completed yet. So now we will consider for a generic random variable x. Okay? So now we will deal with arbitrary random value, may have a negative value, zero value, positive value, just arbitrary. Maybe discrete or non-discrete, continuous, non-continuous. Okay? And we define the positive part and negative part. Okay. All right. So for positive part is that if the value, all right, of the random value at the outcome omega is negative, all right, then we assign x plus to be 0. Okay. But if the original value of the random variable x at the outcome omega is greater than or equal to 0, is non-negative, then we will copy the value there. All right. So we just conserve the positive part. All right. So this is called x plus, the positive part. So the positive part of x. Okay? And we define the negative part, x minus omega. Okay, and we define to be minus x of omega if, oh sorry, I forgot to put, if the original value is negative. Now, so if the original value is negative, then we will change its sign, okay, turn it into positive. But if the original value is non-negative, then we will assign 0 to it. Okay, so we just conserve the negative part. But when we conserve it, we will change the sign of the negative value into positive value. Okay, so that the positive part and the negative part are both non-negative. Okay, so this is called the negative part. Okay, and so we know that both x plus and x minus are non-negative. Random variables. Okay, so they and the original one, the original random variable is actually the positive part minus the negative part. Okay, in any or all outcome in the sample space. Okay. Okay. It's easy to justify for omega such that the x omega is non-negative. Then the positive part is equal to x of the omega. So this is x, the same value. But the negative part, because of that, is 0. So you minus 0. Okay, so they are equal. If for some outcome the value is negative, when it's negative, then the positive part is 0 value. This is 0. And the negative part is minus x omega. So minus minus becomes to positive x omega. Okay, so they will be the same. Okay, so we are using, so for a generic random variable x, we express this random value by the difference of its positive part and negative part. Okay, so we can do this kind of decomposition. Now, the positive part and negative parts are both non-negative random variables. So now we define the expectation of x. So this is by definition defined to be expectation of x, the positive part, minus the expectation of the negative part. This is by definition. Okay, and this definition is meaningful provided that, okay, at least one term on the right, it's finite. Okay? So at least one term, because we have two terms on the right. So at least one term on the right is finite. Right? If both expectation of the positive part and the expectation of the negative part are infinite, then X is said to have no expectation. Okay, so it may happen that for some random variables, this random variable has no expectation. The reason is its positive part and the negative part both have infinite expectation. And so infinity minus infinity is undefined. Okay? But if one of them is finite, right? So for example, this is finite, okay? And this is infinite. Then if positive infinite minus a finite number is also positive infinite. And then expectation of X has infinite, positive infinite expectation. The other hand, if this is finite, but this is infinite, then we will say that the expectation of X is minus infinite. Okay. All right. So in either case, we say X has expectation. Okay. But this expectation is not a finite value, either positive infinite or negative infinite. When both of them are finite, of course, if both of them are finite, then the difference is finite, and the expectation of X is a finite number. So then in that case, we say random variable X has finite expectation. Okay? So a consequence is here. Okay. Before that, I will say, now, since the absolute value of X is equal to the sum of positive part and negative part. Okay. So we have expectation of X is equal to, maybe I will show it later. Yeah, because I will show it later. Maybe okay, just here. Okay, so that's X has finite expectation. So X has finite expectation if and only if both the positive part and the negative part have finite expectation. Okay, so from definition here. Okay, so now we complete our mission at this point, right? So we are able to define the expectation of arbitrary random variables. Okay, and we know how to compute it. Okay, if it has really has expectation. Okay, so there is a possibility that a random variable have no expectation if both of positive part and negative part have infinite expectation. Okay. Okay. So we actually our goal is reached. And okay. Any questions? All right. And so if so we will take a short break for 5 minutes. Okay. All right. So let's continue our discussion. So now we have developed okay. So we developed the expectation of a genetic random variable. Okay, and so now we will extend lemma 5.2.1. So proposition 5.2.e. Okay. Now for any random variable x, okay, the expectation of x, okay, can be written by two integral: probability of x greater than little x dx minus from minus infinity to up to 0 probability of x less than equal to little x dx, provided that at least one term on the right is finite. Okay. All right, so this proposition is actually a reflection of this definition. Okay, so what we want to show is to show that this expectation, the expectation of the positive part of a genetic random variable is actually equal to this integral. And we will show that the expectation of the negative part of a genetic random variable is equal to this integral. Okay, so right, all right, and so this is would be so in terms of CDF, this would be okay. So in terms of CDF, we have here. All right. All right. So okay. So now expectation of x plus x sinks both x plus and x minus are non-negative by lemma 5.2.1. So we have that expectation of x plus is equal to 0 to infinity probability of x plus greater than t and the dt. Okay. Now, but in this event, the value, okay, the t is from 0 to infinity, right? So that the value should be positive, right? So this is always positive. So by definition, this event is equal to x greater than t. It's equal. Since things. The reason is that omega is in X. Okay? If and only if, right? For t greater than equal to 0. Okay? You may see here. This means that x omega is greater than t. And this is so that x of omega is equal to its positive part. Sorry. So that so this is the same. Okay. So the positive part is greater than t. So that greater than 0, right? So this is positive. So when it is positive, then the value is equal to x of omega. Okay, you can look at here. There was the same if they are non-negative. So if the value is positive, all right, that means that x omega must be positive and they are equal. Okay. All right, and so that means that omega is in x greater than t. All right, so this is if and only if. So that means that these two events are the same. Okay, so x plus greater than t, this event is equal to this event. Okay. Now, similarly, okay. So now the negative part is positive. The negative part is positive. It's positive. If and only if the original value x of omega is negative, right? It's negative. So this is probability of x minus x is greater than t and the dt here. Okay. Now, so x will be greater than equal to minus t and the dt. All right, and then we let x to be minus t. Okay, so dx is equal to minus dt. Okay, and so this is becomes to 0 to minus infinity probability x greater than little x and minus dx here. All right, and so we reverse the direction. So this is minus here, probability of x greater than little x and the dx here. All right, so we have that. So this expectation is equal to this one. Now, but this is not a good, the integrand, if you want to express the integrand by the CDF, you know, as we know, this is, what is that? This is equal to the limit the f of x So, I'm sorry. It's less x. Sorry. So this is minus x. Okay. So you have to take the left limiter. Okay. So it's not a good one, right? It is not a good one. But as we know, the probability mass function of x is people. Okay, so this is the probability mass function. This one? Yeah. Yes. Thank you. Thank you. All right. So this is probability mass function. Okay. And we know what is that? This is the minus. Okay. Now, which it's 0 except at x, where jump occurs. Okay. All right, so the probability mass function is 0, equal to 0, except at x where a jump occur, right? Means that when you have a discontinuity at x, but since we have only things they are only countably many discontinuity, many points of discontinuity. For the CDF, okay. P of x, the probability mass function, it's 0 except at the most countably many points. Okay, so that if we integrate only from minus infinity to 0 of p dx, this must be equal to 0. All right, because the integrand may be non-zero at countably many point only, and each point has length 0. Okay, because this is differential, this is the length. All right, so that the integral is 0, must be 0. Okay. All right. So this implies that the integral So this implies that the expectation of the negative part, which we have just shown to be probability of x less than little x dx. Okay? We can add probability of x equal to little x and the dx, and because this integral is 0 together. All right, and so now we can add the integrand together. So this is the equal to, and okay, so it's much better because we don't need to use the left limit of the CDF. Okay, so the expression becomes much simpler. Okay. Okay. All right. So now expectation of x is equal to expectation of x plus expectation of minus, and so this is becomes 2 minus okay, provided that at least one term on the right is finite. Okay, so we compute the proof. Now we want to combine these two integrals into one. Okay, we would like to combine them into one. All right. So, but before that, we need the following proposition result. Okay, so we state it as proposition 5.2.f, right? Says that, so let x be a random variable such that the improper is finite. Okay, so suppose x is a random variable, okay, and when we evaluate this improper Riemann-Stieltjes integral, it's finite. Okay, then we have the result that the limit of x 1 minus f of x, just to say probability of x greater than little x, x goes to infinity. This is equal to 0. Okay, so of course that if x goes to infinity, then this event goes to the empty state, so the probability goes to 0. Okay, but the x goes to infinity, right? So you have infinity times 0. So what is the limit? So you don't know, right? In general, right? But if we know this is the result, if we know this is finite, then we are sure that even though x goes to infinity, but because this one goes to 0 faster than this one, so the product goes to 0. Similarly, we have the same result. So x goes to minus infinity, x, and the probability of, okay, the same. That if x goes to minus infinity, of course this event goes to empty state, and so that the probability is equals to 0. But the x goes to minus infinity. All right, so you have minus infinity times 0. So what is the limit? All right, the result is that even x goes to minus infinity, but this probability goes to 0 faster, okay, faster than x, so that this product goes to 0 too. Okay. All right. But the importance is that you have to know this Riemann-Stieltjes integral is finite. Okay. And the proof, all right, will be omitted because that it need to develop some tools, but I think it's not essential for our course. Okay. Okay, but I need this result. I need this result. Okay, sometimes it will help you. It will help you to know that if this is indeed the case, then this probability goes to 0 faster than 1 over x. Okay. Okay. Similarly, the CDF goes to 0 as x goes to minus infinity, goes to 0 faster than 1 over x. All right. Okay, so now I will prove 5.2.g. If so, let x be a random variable, okay, such that the Riemann-Stieltjes integral okay, so this Riemann-Stieltjes integral is finite. Then the expectation of x equal to the Riemann-Stieltjes integral here. Which is finite. Okay. All right, so now we will use this proposition because we expressed E of x to be this integral minus this integral, right? Okay, so first of all, by integration by parts, okay. So you can go back to look at the lecture notes I distributed to you on the Riemann residual integral. That 1 minus f of x and dx, okay. This one, because this is an improper integral, so it's a goes to infinity, goes a. Okay. All right, and so the limit a goes to infinity. Okay, and by integration by parts, we have x and 1 minus f of x 0 to a plus x d f x, okay. All right. Okay. Oh yeah. Thank you. Thank you. Thank you. When you use remember the integration by parts, it's Theorem 8, right? And it require, remember, let's say, all right? It says that F, G, they are monotone increasing function, right? On AB. So it requires F and G monotone increasing function because they will be, both of them will be used as integrator. So that, okay. Then if G belongs to the R AB relative to F, then we know F well belongs to, so it's a Riemann residual integral over AB relative to G, okay, and we have, so the important thing is here. And we know at AB, G, dF plus AB, F, dG, all right, is equal to FB, GB minus FA and GA. Okay. All right, so we require the integrand and the integrator are both monotone increasing. But look at here. This is monotone decreasing, right? Because when this is up, the difference becomes smaller and smaller, right? So this is monotone decreasing. But x in linear factor, this is monotone increasing. Okay? So to use that, to have the integration by parts, the G should be minus, you have to use G is minus 1 minus F. Use the negative part. You change the sign. When you change the sign, monotone decreasing becomes monotone increasing. On the other hand, if you change the sign, monotone increasing becomes monotone decreasing. Okay, and the F because we use X, okay, the linear function. Okay, right? Remember, so when you use the integrating by part, you have to G defined to be this monotone function, and this F will be the linear function. Okay, and you will have the result. Right? You will have the result here. Okay. So even though you know the theorem, how to use it, right, is an art. Okay, it's an art, right? I think you know what I'm saying. Okay, so that, and you see, this is 0, right? 0 here. So you have limit a goes to infinity, and x 1 minus f of and 1 minus f of x. This is the probability. This is a, and x greater than a. Okay, and plus limit a goes to infinity. Okay, here. But by this proposition here, okay, when a goes up to infinity, this is 0. Okay, so we have 0 plus this improper integral. Okay, and so we have x. So we have infinity x d f of x. Okay. Okay, so now we have expressed this Riemann integral into Riemann's tutorial integral here. The integrator becomes, we use the CDF of x as the integrator. And similarly, and we have to show, we see that this one is finite. Since that okay, since this integral is less than this integral, okay, so this is a finite value. And all right, so now we have more direct maybe I use A and A goes to minus infinity. Okay. Okay, and now by integration by parts, okay, we have x minus okay by integration by parts again. Now f of x is already monotone increasing. X linear function is also monotone increasing. Okay, so we can apply the theorem 8 directly. Okay, and so 0 is here, and so we have a limit a goes to minus infinity, and a fx of a here minus limit a goes to minus infinity 0a, and x df of x here. Again, by this proposition 5.2.f, this is 0. Okay, and so this is becomes to minus. Okay, so this is minus x and df of x, which is 0, which is finite, since less than equal to okay, and so finally e of x is equal to so together minus, so together we have minus minus, so we have okay, and you have done. All right. So if we are able to evaluate this Riemann-Stieltjes integral, and we make sure that it's finite, then the expectation of x can be evaluated similarly by this Riemann-Stieltjes integral, and the integrand is not absolute value of x, but just x here. Okay. All right, and so a consequence of this result now, if x is absolutely continuous with a PDF f of x, then then the CDF of X, okay, has a non-negative derivative f prime x, which is equal to this PDF almost everywhere on the real line. Okay, so that and by Theorem 6 in the in my lecture notes, in a brief on the Riemann Stiegler just integral. In this lecture notes, right? So the expectation, because this is the integrator can be replaced by its derivative, and so because the derivative is equal to this PDF f of x almost everywhere, okay, so we can replace the derivative by f of x, this PDF, because they're almost equal, except points. The total length is equal to 0. Okay. Okay. And so that the evaluation for an absolute continuous random variable can use the PDF to compute. All right. All right. So so we have this one, okay, which exists and finite, right? Provided that the integral converges absolutely, i.e., the integral is finite. Okay. So in general, we usually first evaluate this improper Riemann integral. Okay. And if this is finite, then we are sure that this Riemann integral is also finite. Okay, and this Riemann integral is equal to the expectation of x. Okay, all right. So I stop here. Any questions? Okay, so I start with a general setting, right? Start with a general setting, and to give you the idea how to define the expectation of a generic random variable. Okay, and then come up with the traditional one. First of all, we can reduce to a version by using the CDF, so that in this version we express the expectation of a genetic random variable as a Riemann-Stieltjes integral, and the integrator is the CDF of the random variable. Okay, and this expectation is finite. All right, and this will be true when this Riemann-Stieltjes integral is finite. Okay, it's finite. And then if the random variable is absolutely continuous, then we have a more convenient formula here. Okay, by using to evaluate the expectation by using its PDF. And this is purely Riemann integral, right? Riemann integral you can evaluate, provided that this Riemann integral is finite. Okay, provided this is finite. All right. So that so this has become two special cases. Okay, and then for general random variable, you know an approach to compute its expectation through its positive part and negative parts. And for the positive part, you can using quantization approximation, right, to compute its expectation. And for the negative part, you also, because negative part is also non-negative, so you can using a sequence of simple random variables, okay, to compute its expectation, all right, as precise as you want to. Okay, so that it's the general approach to deal with the problem. Okay, all right. So I stop here and I see you on Thursday.